Hello, my name is Tawanda Zamudzi, and I'm going to give a brief introduction to Fourier transform infrared spectroscopy, sometimes simply referred to as FTIR. Infrared spectroscopy is based on the interaction between infrared radiation and matter. A simplistic way of describing this is that when an infrared beam strikes a sample, one of three things could happen. The beam could be reflected, it could be transmitted, or it could be absorbed. And the goal of an infrared experiment is to measure the reflected or transmitted beam in order to obtain the frequency and intensity of infrared radiation absorbed by the sample. In practical terms, this means placing the sample in the path of an IR source, which is typically a heated silicon carbide rod, and measuring the reflected or transmitted beam at an infrared detector. When IR radiation passes through the sample, some energies of that light are absorbed, and the energies absorbed correspond to the frequency of molecular bond vibrations in the sample. This energy absorbed by the vibrating molecule is therefore missing in the transmitted beam, which is converted to an electrical signal at the detector, allowing us to plot a graph of IR frequency versus intensity. Historically, in FTIR, data is presented as a plot with wave number on the x-axis with units of inverse centimeters. The y-axis could be transmittance, in which case we see dips where the sample absorbs IR radiation. The y-axis could also be in absorbance units, in which case we see peaks where the IR light is absorbed. Whether the y-axis is in transmittance or absorbance units is purely a matter of personal preference. You can get both qualitative and quantitative information from FTIR. In terms of qualitative analysis, the frequency at which the bond vibrates, which is what gives us those peak positions, depends on a couple of factors. The first factor being the bond strength. As the bond strength increases, the frequency at which we see a peak also increases. So this allows us to tell the difference between an alkane, an alkene, and an alkyne, for example. The second factor is the reduced mass, which is an average of the atomic masses of the bonded atoms. The higher the reduced mass, the lower the frequency at which we observe a peak. And this allows us to distinguish between different species bonded to carbon, for example. So we see a lower frequency for heavier atoms bonded to carbon and a higher frequency for lighter atoms bonded to carbon. Qualitative analysis is done on the basis of peak position, peak shape, and peak ratios. In the case of cyclohexanol, we see a characteristic broad OH peak centered around 3,400 inverse centimeters. We also see two sharp CH stretches centered around 2,800 inverse centimeters. Most of the structural information is contained below 1,800 inverse centimeters, and this region is often referred to as the fingerprint region. Overlap of peaks is common in FTIR, which does somewhat complicate data interpretation. However, there are spectral databases out there that can help identify unknowns. Quantitative analysis is on the basis of a relationship known as the Beer-Lambert equation. As IR light passes through a sample and is absorbed, the absorbance is proportional to the concentration of absorbers in the sample, the path length or thickness of the sample, and a property that is unique to each sample known as the molar absorptivity. In practical terms, what this means is that when the sample thickness is constant, the absorbance is directly proportional to the concentration. And as a result, obtaining pseudo-quantitative information is relatively straightforward. And this is accomplished by directly comparing peak areas or absorbance values. So in this example here, the relative analyte concentration was determined by integrating the area of the peak. And a smaller peak area corresponds to low concentration, while a higher peak area corresponds to a higher concentration. For truly quantitative information where physically meaningful concentration units are required, a calibration curve must be constructed using standards where the concentration of those standards is precisely known. And once we have a calibration curve, it is possible to calculate the concentration of the unknown by interpolation into that calibration curve. FTIR has several advantages. It is relatively fast. Analysis takes the order of minutes. There is little to no sample prep required. It's easy to adapt for in situ applications, non-destructive, and can be extremely surface sensitive. The disadvantages of FTIR is that interpretation of spectra can be time consuming. True quantitative analysis can be difficult, and FTIR is extremely sensitive to carbon dioxide and water vapor, which means we have to take that into consideration when designing an experiment. FTIR also does not give any elemental information. Typical applications of FTIR include identification of functional groups, structural elucidation, determination of impurities, determination of orientation, catalysis, process monitoring, and polymer characterization. Here at the MCL, we have 3 instruments which combined can cover near IR, mid IR, and far IR. We also have in situ capabilities which allow us to heat and cool samples, control the atmosphere in which we run our samples. We also have microanalysis capabilities which allow us to map samples using a focal plane array detector.